So let's get started. So this is a crash course on the nuclear chemistry. So this week you have talked about nuclear chemistry and then continue to work on the transition metal chemistry. So nuclear chemistry is an understanding these languages, what is called alpha, beta, and gamma ray, and then also the nuclear symbols. It comes from the Rutherford experiment. And at that time, people didn't have a good understanding about what kind of things that they are doing it. So there was a time that people, discovered the atom structures and so on. So they didn't know what to do, so they just name it as alpha, beta, gamma. So we just have to be, the first one is the alpha, and that happened to be the one that's shown up here. Helium is a positively charged helium nuclei. So it has a mass of the 4, but it's atomic number 2 of the charged particle. And the beta was just actually in these days, you could have just called it as an electron, but at that time, they just called it beta. And then the third one is the gamma ray. Gamma ray is, you probably remember in the Chem 1 class, is a part of the electromagnetic spectrum. So energy is an h nu, right? And so it's a part of the light. And the gamma ray is a very dangerous high energy beam. And the nuclear symbol, this is just the languages for you two guys to get familiar. And proton, neutron, electron, those are probably the most common one that you have seen before. Right? Proton has a mass 1 and Z number 1. Neutron has no protons, so Z number is 0. Whereas the mass is 1. Electron, they have virtually no mass, so it's a 0. Whereas the charge is instead of number of proton, that's a charges. So they put a symbol -1 there to kind of compensate the how many proton, which is a positively charged species in the nuclei. So some form of the nuclear reaction, they can actually emit the electrons. They can emit the other side of the electron, which is sort of, people call it an antimatter. If you're looking at here, it's the same notation as you can see. The electrons are here, electrons are there. That's why it's called a beta, and beta is the same. But they are using this notation, and I don't think they are using this notation to avoid the confusion. The opposite of the electron is what is called a positron, and if you're looking at it, it has no mass, but it has a charges of 1. So it's almost like a proton without charges, right? But they don't want to relate this one to the proton, but with the electron. So this get familiar with a notation called a positron, and is a beta, is an electron. Beta plus is a positron, and alpha is what we talked about. It is a helium, and they are typically positively charged. This one's negatively charged, and this one is positively charged, and so on. And this is a good, I kind of steal some slide from the Kathleen's class, and you start to get to familiar yourself with this notation. Beta emission, okay, so electron emission. Electron, no mass, -1, right? Positron emission, positron is beta plus, and that was a 0 plus 1. Electron capture is an opposite of the emission. So this one is shown up on the other side, right? So they can write it E or they can write beta. It's the same thing. Actually, people probably write this one more, whereas a capture is happening before. Okay, so this is, I guess, happening slide 69. So this is an electron capture can be made, and for example, the proton meet with the electron, and then this sort of the number of proton or charges is compensated to have no net charges, whereas atomic mass is 1, right? So that's we call the neutron. So you just trying to find out what's that correlating this species. is actually these are the answers for the first problem in the week 11's the what you call radio active decay, how to balance those reactions, and then it's we wanted to find out how this one works out, and this let me bring this attention to the one that shown up. I showed it in the earlier times. Oh, I didn't put that in. Sorry about that. So is what I see is this is a notation. When you see this number, this is an atomic numbers, and then that's a notation. So I'm going to kind of color this one in the same way, so you can see that this what I colors in green goes side by side. They show the essentially atomic number, shows how many protons are there, and then I am going to use this one. The one on the top is essentially number of protons plus number of neutrons, right? So then from this notation, you can kind of find out this is a sort of the what they call Z, but I like to just say P, which is the number of protons. And this is an alpha emissions, and then so therefore 94 minus 2, you ended up getting. So the way that it works out is 92. Okay, so 94 is 2 plus 92. So okay, so if I have a proton 94 in the beginning and lose 2, and I should have generate the atoms with atomic number 92. And then all you got to do is, I think I have a periodic table here. So where's a 92? Oh, 92 is right here. So therefore, okay, I got the 92 here, and that's the what I call say uranium. So then I'm going to back to the using the symbol U, right? So that's how you write this one, and then you kind of finish the second step, which is counting the everything, the heavier nuclei elements, which is 2, 4, 2, and 4. So that's 242 minus 4 is 238. Okay, so this is the same thing. If they define that, okay, the electrons are coming out, so 12 and 12 minus 1, that means originally you should have a 13, and 13 is a number that where you start. So this is where you guys start by count balancing the number of quote unquote protons or the charges. So of in the nuclei section. So therefore, this is a nuclei, and then this is all what I call the radioactive decay mode, and something that we can continue to talk about. So please have a look at it, the YouTube videos, and how this is being solved. And if you have questions, and I will be happy to answer that. But I think that most of you know it already. If you look at it, look at the questions, that's pretty clear. Okay, so I think that I kind of mentioned before, but I want to emphasize. If you look at that, the electrons are happening before the arrow. This is essentially this argon with this nuclei react with electrons. So this is what we call. What do we call this? This is an electron capture, right? So sometimes they ask you, this is electron capture, write it the equation, or sometimes actually what kind of decay mode, that's an electron capture. Whereas in this side, you will see that after the arrow, you see the electrons, right? And other compounds. So this is what I guess emission of the electron. Oh, this is this is an emission of a positron. I should have looked for something that more kind of counterpart. So this is an electron, but this is being now emitted, right? Whereas this one was captured, so it happened before or after the reactions, and that's what this is. So let me actually jump onto this, showing you guys a table on here. This is actually one of the tables that from your class, and it kind of nicely summarizes alpha, beta, gamma, and also the positron emission and electron capture. And they essentially show you that, okay, decay means you're losing it, so your essentially A, which is n plus p in my notation, and the Z, which is not strictly proton, but it's sort of the p, right, charges. So you're anticipating you're losing 2 proton, which is a helium, is going to have it with an atomic mass of 4. So that's what is on alpha ray, and sometimes people call it helium 4-2, 2 plus. Okay, that's 2 charges, but it's actually the real reaction is 2 plus 2, and this is a negative 2, and people in these alpha cases they don't show the essentially the charges that they became neutralized. Okay, so to make it clear, what I'm saying is 234. Oh, sorry. Okay, 234.90 TH is 2 minus, and then later the people say, well, I will not writing this way. Okay, and so that's what you see here in the red color. Beta emission, which is an electron, that's what you see, right? Let me blow it up for you. And this gamma has a funny notation because it doesn't have any mass. It does not have any change in the atomic numbers. So it's just the gamma is nothing but the electromagnetic wave, h nu, right? So, and that's the one. And positron, you just get yourself to used to it. Positron is this. So therefore, your atomic number. Actually, the overall, there's no mass changes. Positron do not have mass changes, but atomic number is decreasing it. Electron capture is essentially happening before, and no mass changes, but essentially decreasing from left to right. But try not to remember this kind of the rule that is shown up here. I would rather just understanding alpha is helium, beta is electron, gamma is just a light, and positron and capture is I guess the electron is used as a reactant. So you can just kind of understanding this as well. This is kind of interesting, and then I think the worthwhile for you to remember some higher level questions in nuclear chemistry. You need an understanding on this. For the elements up to Z is 20. If you look at here, so let me blow it up. So this is a number of proton, means essentially this is an atomic number, right? So the up to 20, 0 to 20, you will see people find this is a result. This yellow line is what is most abundant in the nature, and we empirically find out the number of the number of protons and the number of neutrons are the same. Okay, so up to element 20, the Z number 20. So if you go up to, what is a 20? This is up to 20. Okay, so up to 20. And you will see that most abundant one. This is quite a most common choices. So up to element 20, you will have about equal numbers. That's why you are seeing this calcium 20. Most abundant is actually 2020. That's a 40 neutron plus the protons, right? And the exception to this rule is this one. And you see these atomic numbers are not exactly the integers because there is always an abundance of different isotope. And that's why you guys are seeing this. But the rule of thumb is up to here is good to know. Same number of neutrons and protons. And then they start to deviate from the top portion, right? So what's actually important for me to remember also is 20 to 40 is a little bit more and more. But what's important here is if you look at this section here, and that's the one where neutron numbers are smaller than number of protons, and that's not really favored. Oh, not the other way, right? Okay. This makes it very, very unhappy scenario. So that's not what they do not like this. Okay, so instead of put a star, I put this the one that they try to avoid it. Okay, so they don't mind having an extra neutrons in many, because if you look at this trend, but this other side is not so good. Okay, so just remember that sometimes this is quite useful. I think that this is where I want to stop now. What I didn't record it here is in this section is I didn't do the half-life problem, and that's the one I'm going to record it in the another section on the one, and then I'm going to post it both of them. So this time I'm just focusing on the notations, and particularly this concept about this you don't want U1. Usually the neutron numbers are same or higher, right? So this is a same or higher. And also anything that when Z is bigger than 83, and that's where you are seeing this, the periodic table 83, and so that's from here. Oh, is it 83? Yeah, 83, which is, and so anything down here, right? And then something here, anything down here. This is all the things that is very not so stable, so they like to decompose and then do a lot of unstable. So it is elements, and it's a very difficult compound element nuclei that can emit the electron, emit the protons, and there's a lot of complex scenarios.